Welcome, Axor, Galactic Observatory. Tonight, the story begins deep beneath Earth's oldest layers, where strange clues seem to whisper that human civilization may not have been the first to shape this planet. Hidden in stone, fossil gaps, isotope anomalies, and ancient mass extinctions lies a mystery that challenges everything believed about Earth's past. This documentary moves slowly through the buried evidence, following the possibility of forgotten technological traces, vanished worlds, and the silent record left behind in rock, ice, and ocean sediments. It is a journey through deep time, where science meets one of the most unsettling questions ever asked. Before beginning, please take a moment to like this video, subscribe to the channel, and support more deep space, ancient Earth, and science mystery documentaries like this one. Now, the surface falls away, the ages open beneath our feet, and the search begins. At the surface of the planet, the ground appears quiet and ordinary, a thin living skin made of soil, sand, river silt, coastal mud, and weathered stone. It holds forests, grasslands, roads, cities, and farms. Yet beneath these familiar forms lies a far older habit of storage. Earth keeps records. It does not keep them in sentences or in carved monuments that remain unchanged through time. It keeps them in layers. A river floods and leaves behind a film of sediment. A volcano spreads ash across a continent. A forest burns and its smoke settles into lakes and peat. Tiny shells sink through dark water and gather on the seafloor. Dust from distant deserts drifts through the atmosphere and comes down over ice or ocean. With enough time, these thin deposits become compacted, buried, altered, and folded into the crust. Yet some part of their original story remains. Geology begins with this simple fact. The planet is always writing, and the writing is physical. A boundary in rock can mark a drought, a flood, a shift in temperature, a chemical change in the sea, or the aftermath of an impact from space. At first glance, these marks seem mute, but modern science has learned how to read them with surprising patience. Grain size reveals the energy of ancient water, isotopes, which are slightly different forms of the same element, preserve clues about temperature, carbon cycling, and sources of material. Microscopic particles carry the signs of fire, erosion, industry, and even distant explosions. What appears to be a plain cliff face or an exposed road cut is often a compressed archive stretching across thousands or millions of years. The idea that a civilization might also leave traces in that archive begins here, not with ruins or machines, but with the calm recognition that Earth records disturbance wherever disturbance is broad enough, long enough, or unusual enough to interrupt the ordinary drift of sediments and chemistry. The most famous modern example of such a trace lies at the boundary between the age of dinosaurs and the age that follows. In many places around the world, geologists find a narrow layer enriched in iridium, an element that is rare in Earth's crust and more common in meteorites. That layer helps identify the aftermath of a major asteroid impact about 66 million years ago. It is thin, yet it is global. It marks a brief event that altered the course of life. This serves as a useful starting point because it shows that a dramatic planetary change does not need to leave a giant visible scar everywhere in order to remain detectable. Sometimes a subtle chemical line is enough. From there, the surface world becomes easier to see as a map of signatures. Coal ash from power generation settles as fine particles. Soot from combustion enters ice, lakes, and soils. Heavy metals released by mining and smelting spread through watersheds and estuaries. Nitrogen from agriculture changes the chemistry of rivers and coastal seas. Plastics fragment into particles that travel through air, mud, beaches, and deep marine sediments. Concrete weathers, but its mineral balance differs from common natural rock. Even before structures collapse, industry has already translated itself into dust, gas, and chemical shifts. A city does not need to survive as a city in order to persist as evidence. It can dissolve into a pattern. It can become a strange concentration of metals, an abrupt pulse of carbon, a layer of ash spheres formed at high temperature, or an unusual mix of minerals transported far beyond their point of origin. On the present Earth, these effects are not speculative. They are measurable. They enter sediments in harbours, floodplains, and continental shelves. They spread through peat bogs, lake beds, coral skeletons, and polar snow. The surface therefore acts like the first page of a longer archive, one that begins with visible disturbance and then passes the evidence downward into burial. Yet the surface is also deceptive because it is where destruction works fastest. Rain, roots, frost, scavengers, oxidation, and human rebuilding erase shape long before they erase chemistry. The outlines of roads, towers, and machines are temporary. Their transformed remains are more durable. This difference matters because it shifts attention away from the search for obvious ruins and toward the quieter persistence of altered matter. A future geologist might never find a standing building from the present age, but that geologist could still identify a horizon rich in synthetic compounds, combustion residues, radionuclides, and globally redistributed materials. The question of earlier civilizations, when stated cautiously, does not require fantasy about hidden cities preserved intact beneath every desert or ocean basin. It asks something gentler and more rigorous. If a technological society had existed in the distant past, what would the surface world have absorbed from it, and how would those absorbed changes move into the record that geology preserves? Surface processes offer the first answer. Wind lifts particles and carries them across continents. Rivers gather waste and weathered fragments from wide drainage basins. Waves sort material along coasts and bury it in deltas. Wildfire, whether natural or human-caused, leaves charcoal and altered soils. Excavation exposes fresh rock, accelerates erosion, and redirects sediment. Large-scale extraction changes the physical balance of landscapes, while combustion changes the atmosphere above them. None of these pathways is mysterious. They operate now slowly but continuously, turning activity into deposits. Over enough time, the deposits become part of stratigraphy, the ordered sequence of layers that geologists compare from place to place. Surface clues are therefore both local and planetary. A mine-tailing pond may be local, airborne lead can become continental, a single factory is local, a greenhouse gas pulse can become global. This gradation from place to place is essential because geology often gains confidence not from one dramatic object, but from repeated agreement across many distant archives. When different lakes, marine basins, soils, and ice records show the same directional shift at roughly the same interval, the signal grows stronger. The surface begins the process, but correlation gives it meaning. For now, this outermost region remains enough. The visible Earth, with its dust, ash, soils, waters, and exposed rock, already demonstrates the principle that change leaves form, chemistry, and pattern behind. The land does not need memory in a human sense. It only needs accumulation. Every storm lays down another fraction. Every fire writes a dark trace. Every period of stability lets a soil horizon mature. Every disruption interrupts that stability and marks itself through contrast. In this way, the surface of the planet becomes the calm threshold between the living present and the deeper archive below, receiving the first imprint of whatever passes across it, whether that passage comes from ice, volcanoes, oceans, impacts, or the brief industrial restlessness of an intelligent species. Beneath the visible surface lies a slower world where time expands and human scales begin to lose their meaning. Loose sediment does not remain loose forever. Mud becomes shale under pressure. Sand becomes sandstone as mineral-rich water moves through buried grains and binds them together. Layers that begin as soft beds on floodplains, sea floors, lake bottoms, and shallow shelves are gradually pressed, tilted, fractured, heated, and sometimes erased. This long transformation is part of why Earth's past is difficult to read clearly. The planet does preserve evidence, but it preserves selectively. It keeps some signals with remarkable fidelity and removes others almost completely. To understand whether traces of a brief industrial civilization could remain visible after millions of years, geology first has to be understood as a system of both memory and loss. Sedimentation is the first part of that system. Wherever particles settle out of water, air, or ice, the planet gains a chance to store information. A calm lake can capture annual layers so fine that seasonal changes remain distinct. A continental shelf can gather mud, shells, pollen, soot, and chemical residues carried from vast inland drainage systems. A delta can entomb plant matter, minerals, and fragments washed from mountains and cities alike. In these settings, material arrives in sequence. Younger layers cover older ones. If burial continues without major disturbance, the order can remain understandable for very long spans of time. This is why geologists value places where deposition is steady and where later erosion has been limited. Yet deposition alone is never the whole story. Erosion begins almost as soon as deposition does. Wind strips fine particles from dry ground. Rivers cut into their own floodplains. Waves remove sediment from some coasts while piling it onto others. Glaciers grind down bedrock and carry older material into younger deposits. Mountains rise and expose formerly buried layers to weathering, while basins sink and create new accommodation space for burial. The geological archive is therefore incomplete by its nature. It resembles a manuscript copied, torn, buried, scorched, rewritten, and only partly recovered. Many intervals of time are missing in many places. These missing intervals are called unconformities, surfaces that represent a gap in the record where deposition stopped. Erosion removed earlier layers, or both happened in sequence. An unconformity may represent thousands, millions, or even hundreds of millions of years. It is one of the clearest reminders that absence of evidence in one place is not always evidence of true absence across the planet. The deeper one moves into geological thinking, the more important this becomes. A civilization lasting a few thousand years would occupy only a tiny instant against the age of Earth. If all direct structures from such a civilization stood on exposed land, then weathering, tectonic recycling, and erosion could destroy their obvious forms long before the rock record around them had much chance to stabilize. Oceanic crust, for example, is constantly created and destroyed through plate tectonics. Most of the seafloor is geologically young because older oceanic plates are pushed back into the mantle at subduction zones. Any city or industrial complex built on oceanic crust in the distant past could be lost not only to burial, but to complete recycling into Earth's interior. Continental crust is more enduring, but even continents are restless. They split, collide, uplift, drown beneath shallow seas, and undergo repeated episodes of deformation and metamorphism. Rocks that were once near the surface can be buried deep enough to recrystallize, overprinting older evidence. This does not mean all traces vanish. It means traces must be sought in the kinds of signals most likely to survive transformation: broad chemical anomalies, isotope shifts, and sudden changes in sediment composition have a better chance of persistence than buildings, roads, or tools left in their original shapes. This is the central scale problem in deep time. Human history feels long because human memory is short. In geological terms, however, even the full span of cities, agriculture, and industry is a very thin layer. If modern industrial civilization endured for 10,000 years and then disappeared, the interval would still be smaller than many ordinary gaps in stratigraphic records. A single erosional surface in one basin could remove that entire chapter without leaving any obvious local sign that it had ever existed. The challenge is not that geology is empty. The challenge is that geology is vast, patchy, and indifferent to preserving what human beings consider important. Bones preserve better than skin. Shells preserve better than leaves. Mineral changes preserve better than architecture. Global atmospheric disturbance preserves better than local craftsmanship. Burial depth also changes what can survive. In shallow burial, organic molecules may sometimes remain recognizable, especially in cold, dry, or oxygen-poor environments. With deeper burial and rising temperature, many compounds break down or are altered into simpler forms. Pressure squeezes out water, rearranges crystals, and changes pore spaces. Groundwater moves through sediments, adding and removing chemical components. Even without intense metamorphism, the original state of a deposit can be modified substantially. Thus, any long-term search for ancient industrial evidence must consider taphonomy, the study of how biological and material remains are altered from the time of deposition to the time of discovery. Taphonomy is often discussed in relation to fossils, but the same principle extends to any physical trace. A discarded object becomes corroded fragments, a plastic polymer becomes smaller compounds, or a residue with altered structure. Soot becomes incorporated into soil or sediment and mixed with other carbon sources. Metals oxidize, migrate, and concentrate in new minerals. The signal may remain, but rarely in its initial form. Geological time also smooths events. A catastrophe that unfolds in a single year can appear in rock as a thin layer that represents a broader interval because of mixing, bioturbation, compaction, or limits in dating precision. Bioturbation, the churning of sediment by living organisms, blurs boundaries in marine and lake settings. Root growth disrupts soils. Burrowing animals move particles vertically. Later fluids carry dissolved ions across former surfaces. For very ancient intervals, a change that once occurred quickly may only be resolvable as a narrow band, not as a day-by-day narrative. This has an important consequence for the question at hand. A short-lived industrial pulse might still be visible if its effects were global and chemically unusual, but its fine internal details could be lost. Geology may reveal that something changed sharply without preserving a clear picture of how society functioned during that change. Dating methods help constrain these problems but do not eliminate them. Radiometric dating can determine the age of igneous minerals or volcanic ash layers with great power, while relative dating places structure in sequence using fossils, magnetic reversals, and cross-cutting relationships. Still, exact synchrony across distant archives can be difficult to establish. A signal found in one basin may need careful comparison with others before it can be treated as global. This is why robust interpretations depend on multiple independent lines of evidence. A single anomaly may be local contamination, unusual volcanism, or an analytical artifact. Repetition across many settings is more persuasive. The long archive beneath the surface therefore imposes both caution and possibility. It cautions against expecting pristine remains of deep-time civilizations in ordinary rocks. It also allows the possibility that broad disturbances, once translated into atmospheric chemistry, sedimentary change, unusual isotopes, or globally distributed particles could remain detectable long after every direct monument had vanished. The deeper geology becomes, the less it behaves like a museum of intact objects, and the more it behaves like a filtered ledger of planetary transitions. The question is not whether time destroys, it certainly does. The question is, what kinds of disturbance survive destruction well enough to still be read after burial, alteration, and immense spans of silence? In that buried ledger, duration matters, scale matters, and contrast with ordinary Earth processes matters most of all. The Silurian Hypothesis begins not as a claim that a lost civilization is known to have existed, but as a disciplined question about what traces an industrial society would leave if it had arisen long before the present age. Its usefulness lies in method rather than spectacle. It asks scientists to step outside the assumption that humans are the only example of technological activity on Earth, and to examine the rock record in a more general way. If industry changes a planet, then those changes should be describable in terms of chemistry, sediment, climate, and biological response. Once those signatures are described, the next step is simple in principle, though difficult in practice. The record can be searched for similar patterns in older intervals. In this sense, the hypothesis acts as a mirror. It uses the known effects of modern civilization to frame a search for unknown analogues in deep time. The name itself comes from fiction rather than geology, borrowed from an ancient species imagined in a television story. Yet the scientific proposal remains sober. It does not argue that strange fossils or hidden chambers prove anything. It does not rest on myths, monuments, or dramatic objects said to be out of place. Instead, it asks what industrial activity means in planetary terms. A civilization, if it reaches large-scale energy use, does not merely build structures. It moves matter from one reservoir to another. It digs buried carbon from the ground and transfers it to the atmosphere. It refines metals and disperses them. It fixes nitrogen on scales that natural ecosystems cannot match in ordinary balance. It manufactures molecules that do not commonly arise without directed chemistry. It reshapes erosion, redirects rivers, acidifies waters, and leaves a pulse of distinctive residues in the places where sediment quietly accumulates. The hypothesis, therefore, shifts attention away from the imagined survival of artifacts and toward the more durable logic of system disruption. It is easier to erase a city than to erase a planet-wide perturbation of carbon cycling. It is easier to obliterate a machine than to remove every isotopic consequence of prolonged combustion, mining, and industrial synthesis. Framed this way, the question becomes less romantic and more exact. Could a prior civilization have existed briefly enough, or far enough back in time, that its direct remains were lost while some indirect signatures persisted? Scientific discussion of the idea makes clear that this is possible in principle. A short interval in deep time is hard to resolve. Most of Earth's surface is either eroded, buried, metamorphosed, or recycled across long spans. Yet possibility in principle is not the same as evidence in hand. The strength of the hypothesis lies in establishing criteria that evidence would need to meet. For example, one would expect a rapid negative shift in carbon isotopes if a civilization released large amounts of ancient carbon through combustion. One might expect unusual sedimentary particles from high-temperature processes, elevated concentrations of some synthetic compounds, abrupt changes in biogeochemical cycles, or patterns of extinction and recovery associated with environmental stress. A truly advanced civilization might also leave more exotic markers, though caution is essential because the more exotic the marker, the harder it becomes to distinguish from misunderstanding, contamination, or poorly known natural mechanisms. This caution is central to the real scientific value of the idea. It disciplines imagination by forcing it into testable form. It says that if such a civilization existed, it cannot be inferred merely because a gap appears in fossils or because some ancient event remains puzzling. The signatures must cohere. They must be measurable. They must be distinguishable, as far as possible, from volcanism, impact events, methane release, orbital change, tectonic reorganization, and all the other processes already known to disturb the Earth system. This is why the hypothesis belongs more to Earth system science than to traditional archaeology. Archaeology studies direct cultural remains within the comparatively recent past. The Silurian question extends into intervals where culture as an intact material record would almost certainly fail to survive. It therefore asks geology, paleoclimatology, stratigraphy, and geochemistry to play the leading roles. The surface archive, the deep archive, and the atmospheric archive all become relevant. A civilization can vanish in form and still remain legible in altered cycles. This is also where the hypothesis touches planetary science more broadly. Scientists already think in terms of biosignatures and technosignatures when considering other worlds. A biosignature is evidence of life, such as a chemical imbalance in an atmosphere that is hard to maintain without biology. A technosignature is evidence of technology, such as industrial pollution or artificial energy use, applied to Earth. This same framework becomes unexpectedly revealing. It invites the present age to be treated as one example of a planet altered by intelligence. Once that comparison is made, older intervals can be evaluated using similar reasoning. The Earth becomes, in a sense, a nearby test case for questions often aimed at distant planets. At the same time, the hypothesis exposes how strongly observation depends on expectation. If researchers assume from the beginning that no prior industrial society could have existed, then unusual signals will always be routed toward non-industrial explanations, even when the fit is imperfect. If researchers assume the opposite, they risk forcing every anomaly into a sensational narrative. The hypothesis asks for neither reflex. It asks instead for structured neutrality. Start from what industry does. Determine which consequences would endure. Search for those consequences without inflating ambiguity into proof. In that disciplined space, the idea becomes scientifically productive even if the answer ultimately remains negative. It can improve understanding of preservation, sharpen definitions of technosignatures, and clarify how the Anthropocene itself may appear in future strata. The present civilization thus becomes both subject and model, its atmospheric carbon rise, plastic dispersal, concrete production, fertilizer imprint, radionuclide pulse, and extinction pressures provide a library of expected markers. The deeper question is whether any earlier interval presents a combination sufficiently similar to deserve special attention. That search is difficult because natural Earth processes can mimic some industrial effects. Large igneous provinces can drive warming and carbon shifts. Impacts can spread unusual elements and soot. Ocean anoxia can alter sediments and ecosystems on grand scales. Methane release can create abrupt climatic signals. The Earth is fully capable of drama without technology. For that reason, the Silurian hypothesis does not narrow the field of explanation so much as it raises the standard of comparison. A candidate interval would need more than one odd feature. It would need a cluster of linked signatures that collectively resist familiar natural accounts. So far, no accepted interval meets that standard. Yet the hypothesis remains useful because it frames exactly what would have to be found. It converts a vague idea into a research program centered on durability, scale, and signal discrimination. In doing so, it also humbles the present. It reminds modern civilization that what feels singular from within may look brief and fragmentary from the perspective of stone. Even if humans are indeed the first technological species on Earth, the geological record will not preserve that fact in the manner of a written certificate. It will preserve it as a disturbance pattern, layered into sediment and chemistry, waiting for distant interpreters who may know nothing of names, nations, or memory, but who can still read what industry does when it passes across a living world. Industrial activity leaves behind far more than buildings, machines, or altered skylines. Its most durable legacy is a reorganization of matter. Materials that once rested in concentrated geological reservoirs are extracted, processed, heated, refined, transported, dispersed, and finally deposited again in new settings and unfamiliar combinations. This movement is not random. It follows flows of energy and purpose. Ore is separated from host rock. Metals are purified, fuels are burned, minerals are calcined, and raw substances are converted into products whose forms are temporary, but whose residues can persist. In geological terms, industry acts as a rapid sorting and redistribution system. It accelerates processes that nature performs slowly, and it creates chemical associations that are uncommon in undisturbed environments. Mining provides one clear example. In a natural landscape, many metals remain locked within ore bodies, concentrated in particular rock types and buried at depth. Extraction breaks this arrangement. Large volumes of surrounding rock are excavated, crushed, exposed to air and water, and spread across tailings piles, settling ponds, and downstream sediments. Sulfide minerals that were once stable underground oxidize when brought to the surface, generating acidic drainage that mobilizes copper, zinc, lead, arsenic, and other elements into rivers and soils. Even if the mine itself collapses or erodes away, the geochemical disturbance can persist in basin sediments as a distinctive pulse of metal enrichment, accompanied by changes in mineral form and acidity indicators. Smelting and high-temperature processing add another layer of durability. When ore is heated, impurities are separated and gases, slags, and fine particulates are released. These products can travel through the atmosphere before settling into lakes, peat, floodplains, and marine margins. Some of the particles formed in furnaces or power plants are microspheres, tiny rounded grains created when minerals melt and cool rapidly. Their shapes differ from many naturally weathered grains because heat and surface tension have reworked them into smooth forms. Fly ash from coal combustion is a modern example. It can be identified by its composition, morphology, and association with other industrial markers. In the future rock record, such particles could survive burial even after the plants that produced them are gone. Cement manufacture leaves a different kind of trace. Limestone is heated to release carbon dioxide and create reactive compounds that harden when mixed with water and aggregates. The resulting concrete spreads artificial stone across landscapes, river valleys, coastlines, and urban foundations. Over time it fractures, dissolves, and is buried, but its mineral blend, pore structure, and associated reinforcing metals distinguish it from many ordinary sedimentary deposits. Bricks, glass, ceramics, and slags also form recognizable suites of thermally altered material. Once broken and reworked, they may cease to look like artifacts, yet they continue to mark the presence of concentrated heating, engineered chemistry, and large-scale construction. Combustion is perhaps the most globally important industrial process because it turns buried carbon into atmospheric gas, while also producing soot, ash, and altered isotopic signals. Soot consists of fine, black carbon particles formed during incomplete burning. It can travel far from its source, darken snow and ice, and settle into wetlands, lakes, and ocean sediments. Charcoal from natural wildfire also enters the record, so distinction depends on scale, morphology, associated pollutants, and context. Industrial combustion often travels with sulfur emissions, trace metals, nitrogen oxides, and a broader package of residues linked to fossil fuels and urbanization. This package can produce multi-proxy evidence, meaning several independent indicators appearing together in the same stratigraphic interval. Such combinations are often stronger than any single signal on its own. Manufacturing introduces substances that are rare, unstable, or absent in most natural systems. Some compounds break down quickly and may leave little long-term evidence. Others persist or transform into daughter products that remain measurable. Synthetic organic chemicals can sorb onto fine sediment, accumulate in low oxygen settings, or become trapped in soils and ice. Plastics are especially instructive because they combine physical durability with broad distribution. Large plastic items fragment into microplastics and nanoplastics, which then move through water, air, organisms, and sediment. Their long-term fate depends on polymer type, sunlight exposure, oxidation, temperature, microbial action, and burial setting. Many will degrade over time, but some fraction may remain preserved as altered residues, inclusions, or chemically distinctive fragments. Industry also leaves unmistakable marks through landscape change. Forest removal increases erosion. Dams trap sediment upstream and starve downstream deltas and coasts. Channelization forces rivers into new paths and changes floodplain deposition. Groundwater pumping causes subsidence in some basins. Quarrying, tunneling, drilling, and levelling create abrupt topographic rearrangements. While individual cuts or embankments may erode away, the redistributed sediment load and the basin-scale shift in deposition can remain legible. A major dam, for example, can create a lacustrine deposit upstream and a sediment deficit downstream, changing grain size patterns and organic accumulation over wide areas. Agriculture, though older than industry, becomes industrial in effect when mechanization, fertilizers, and monocultures operate at continental scale. The repeated disturbance of soils alters carbon storage, dust production, and sediment delivery to rivers. Synthetic fertilizers increase reactive nitrogen and phosphorus, stimulating eutrophication in lakes, estuaries, and coastal waters. These nutrient surpluses can drive algal blooms, oxygen depletion, and laminated sediments formed under low oxygen bottom waters. Such sediments may later record not only the biological response but also the chemical fingerprint of intensive land use, even absent preserved machinery or tools. The ecological and geochemical signal of industrial agriculture can be extensive. One of the most important lessons from all these processes is that industry writes in both concentration and dispersal. Some residues remain clustered near points of extraction or production, such as tailings, slag heaps, landfills, and urban rubble. Others become planetary, spread through the air, ocean circulation, migratory organisms, and river networks, a technosphere, the total realm of human-made materials and energy flows, does not stay neatly bounded within cities. It leaks, it weathers, it fragments. It enters the same sedimentary systems that preserve volcanic ash, pollen, shells, and dust. Over enough time, the direct shapes of industry may be lost, but its residues endure as abrupt shifts in particle type, mineral association, elemental abundance, and chemical novelty. This is why the geological legacy of a civilization is best understood not as a collection of monuments, but as a stratigraphic pulse. Industry leaves behind altered earth materials, newly combined substances, accelerated transfers between reservoirs, and a broad suite of persistent traces that continue to settle long after the visible machinery has fallen silent. Carbon moves through Earth in several linked reservoirs, and its movement is one of the clearest ways to detect rapid disturbance. Some carbon circulates quickly through air, surface waters, soils, plants, and living bodies. Other carbon remains locked away for far longer spans inside rocks, sediments, and fossil fuels. Coal, oil, and natural gas are ancient stores, built from once living matter that has been buried, transformed, and isolated from the short-term cycle for millions of years. When that buried carbon is extracted and burned, it does more than raise the concentration of carbon dioxide in the atmosphere. It also changes the isotopic balance of carbon in measurable ways. This happens because carbon occurs mainly as two stable forms, carbon-12 and carbon-13. Living systems tend to favour the lighter form, carbon-12, during photosynthesis. As a result, organic matter and the fossil fuels derived from it are relatively depleted in carbon-13. When a civilization burns large quantities of fossil fuel, it releases carbon that carries this isotopic bias. The atmosphere, oceans, soils, and sediments then begin to register a negative carbon isotope excursion, meaning a shift toward lighter carbon. This shift becomes one of the most valuable signatures in paleoclimate and stratigraphic studies because it links chemistry to process. It does not merely show that carbon changed, it suggests what kind of carbon entered the system and how quickly that change may have occurred. In the present age, this is already visible. Atmospheric measurements, tree rings, marine records, and ice cores all document a clear movement tied to industrial emissions. Over longer time spans, similar shifts can be found in sedimentary rocks, fossil shells, organic matter, and carbonate deposits. The challenge is interpretation. Nature is fully capable of causing major carbon disturbances. Large volcanic provinces can release massive amounts of carbon dioxide directly, and can also warm the planet enough to trigger secondary releases of methane and organic carbon. Rapid warming can destabilize methane hydrates in marine sediments. Tectonic change can expose organic-rich rocks to oxidation. Ocean circulation shifts can alter how carbon is stored in deep waters and returned to the atmosphere. For this reason, a carbon isotope shift alone cannot demonstrate industrial activity. Yet it remains central because any civilization powered heavily by fossil carbon would almost certainly create one. Carbon therefore becomes both a clue and a test. If there were an ancient industrial society, a negative isotope excursion would be expected. If such an excursion exists, it must still be weighed against volcanic, climatic, and tectonic alternatives. The geological record contains several intervals where carbon isotopes shift rapidly toward lighter values, often accompanied by warming, ocean acidification, ecological stress, and extinction. Among the most discussed is the Paleocene-Eocene thermal maximum, roughly 56 million years ago, when global temperatures rose sharply and carbon moved through the Earth system in a geologically abrupt pulse. Marine sediments show dissolution of carbonate on the seafloor, indicating acidification. Terrestrial records show migration of plants and animals. The isotope signal is clear. Yet the favoured explanations remain natural, involving large carbon release from volcanic activity associated with the North Atlantic igneous province, possibly combined with methane or organic carbon feedbacks. This interval is important not because it points strongly to a lost civilization, but because it provides a real example of how a rapid carbon disturbance looks in rock. It offers a comparison for what industrial forcing might resemble, and where the similarities stop. The end-Permian crisis, about 252 million years ago, offers an even more severe case. It is marked by one of the largest mass extinctions in Earth history, major warming, widespread oxygen loss in the oceans, and significant carbon cycle disruption. Carbon isotope records show a marked negative excursion, and the Siberian Trap's large igneous province is widely considered the driving force, possibly amplified by feedbacks from coal combustion, by magma intrusion, methane release, and ecosystem collapse. Again, the significance lies in the pattern. Carbon shifts often travel with a suite of consequences, including temperature rise, acidification, altered weathering, and biological turnover. Any ancient industrial episode would likely create a comparable bundle, though perhaps on a different scale and over a different duration. This is why carbon records cannot be read in isolation. Timing matters, magnitude matters, recovery time matters. Associated sedimentary and ecological signals matter as well. Carbon also enters rocks in more than one form, and each archive has its own strengths. Marine carbonates record the chemistry of seawater and can provide long, correlated records across basins. Organic-rich shales preserve carbon from biological material and can be sensitive to local productivity and oxygen conditions. Soil carbonates reflect conditions on land, especially in dry regions. Plant fossils and biomarker molecules can reveal ecological responses and sources of organic input. No single archive gives the full picture, but together they can trace how carbon moved between air, ocean, land, and life. In a search for possible technosignatures, this multi-archive approach becomes essential. A true industrial perturbation would not remain confined to one environment. It would likely show itself in atmospheric proxies, marine chemistry, sediment composition, and biological stress markers across broad regions. Another important factor is duration. Human emissions are occurring extremely quickly by geological standards, concentrated over a few centuries. In deep time, however, even a fast event may be blurred into several thousand years depending on the resolution of the record. A civilization that burned fossil fuels over a comparatively brief interval could therefore leave a carbon pulse that looks geologically abrupt but not instantaneous. This blurring complicates direct comparison between modern records and ancient strata. Even so, the shape of onset and recovery may still offer clues. A sharp rise followed by a prolonged recovery can suggest a strong, rapid input followed by slower removal through weathering, carbonate formation, and biological uptake. Carbon is therefore one of the most powerful guides in the buried archive because it links energy use to planetary consequence. It reveals how combustion at scale becomes chemistry at scale. It enters air, dissolves into rain and seawater, alters acidity, changes isotopic ratios, affects temperature, shifts ecosystems, and eventually settles into stone. For the Silurian question, carbon does not provide an answer by itself, but it defines one of the clearest paths by which an industrial society would become legible after its visible works had vanished. If industry passed through deep time and fed itself on ancient fuel, the rocks would have reason to remember. The atmosphere is the thinnest major envelope of the planet, yet it is one of the most sensitive recorders of change. It responds quickly to shifts in energy use, chemistry, land cover, volcanism, impacts, and biology. And although air itself does not remain fixed in place, traces of its past composition can be preserved in other materials with remarkable fidelity. Ice is one of the clearest examples. Snow falls, accumulates, compresses, and slowly turns to glacial ice, trapping bubbles of ancient air as it densifies. Those bubbles preserve direct samples of former atmospheres, allowing measurements of carbon dioxide, methane, nitrous oxide, and other gases over long intervals. In polar regions, especially where accumulation is regular and melting is limited, ice cores become layered archives of atmospheric history. dust blown from distant continents settles onto the snow, sulfate from volcanic eruptions forms acidic horizons, soot, sea salt, pollen, and industrial aerosols are added in varying proportions. Each layer therefore holds both the gases of the air and the particles that travelled through it. In the recent record, this sensitivity is unmistakable. Industrial emissions appear as rising greenhouse gases, lead from gasoline, sulfate from combustion, black carbon from burning, and radionuclides from nuclear testing. The atmosphere does not keep these changes to itself. It distributes them, dilutes them, and then hands them to ice sheets, peat bogs, lakes, cave deposits, marine sediments, tree rings, and soils. This capacity for broad dispersal makes the atmosphere a powerful conveyor of planetary signals. A civilization that changes the air at scale does not leave evidence only where its cities stand. It leaves evidence wherever the air carries its products, and wherever those products are captured by sediment or ice. Yet atmospheric archives extend beyond frozen bubbles. Some minerals form in equilibrium with the surrounding air and retain isotopic or chemical information about humidity, temperature, and gas composition. Soil carbonates can reflect the balance between atmospheric carbon dioxide and biological respiration in the ground. Stomata, the tiny pores on fossil leaves, vary in density depending in part on carbon dioxide levels, offering an indirect biological proxy for ancient atmospheres. Marine sediments record how gases dissolved into surface waters and altered ocean chemistry. Speleothems, mineral deposits growing in caves, preserve signals of rainfall source, vegetation change, and broader climate conditions that are linked to atmospheric circulation. Amber can trap minute samples of gas, though interpretation of such material is often difficult and requires caution. Together, these archives do not provide a perfect film of ancient air, but they offer overlapping glimpses, and when several proxies agree, confidence increases. From the perspective of technosignatures, the atmosphere matters because industrial activity alters it through several distinct pathways at once. Combustion increases carbon dioxide and often methane through leakage and land disturbance. Fertilizer use and high-temperature burning raise nitrous oxide and nitrogen oxides. Smelting and fuel combustion release sulfur compounds, particulates, and trace metals. Synthetic chemicals, depending on the technology involved, may add molecules that rarely arise in nature. Land clearing reduces or rearranges biological uptake and changes the reflectivity of the surface, which feeds back into regional climate. A civilization engaged in deliberate climate modification could also inject aerosols, release engineered gases, or alter the balance of clouds and surface albedo. These actions would not all preserve equally well, but some would almost certainly register as unusual combinations of gas shifts, particle deposition, and isotopic change. The critical point is that the atmosphere integrates many local activities into a planetary expression. A mine is local, a refinery is local, a power plant is local. Their collective effect on air can become global. This is why the atmosphere often preserves broad coherence more effectively than the surface alone. It smooths geography while still recording source signatures strongly enough to remain measurable. Interpretation remains difficult because natural processes can also change the air dramatically. Large volcanic eruptions inject sulfate aerosols, carbon dioxide, halogens, and ash. Flood basalts operating over long intervals can elevate greenhouse gases and alter climate profoundly. Wildfire episodes increase soot and carbon monoxide. Methane release from wetlands, permafrost, or marine sediments can raise greenhouse concentrations. Changes in vegetation cover driven by climate or evolution alter oxygen and carbon dioxide through photosynthesis and respiration. The Great Oxidation Event and later oxygenation Steps in Earth history show that biology itself can transform the atmosphere on planetary scales. For this reason, no ancient atmospheric anomaly can be treated lightly as evidence of technology. The strength of an industrial interpretation would depend on patterns that are difficult to reproduce through ordinary volcanism or biosphere feedback alone, such as sharply coordinated appearances of unusual compounds, isotope combinations pointing to specific reservoir transfers, or repeated multi-proxy packages that indicate directed intervention rather than broad natural forcing. Even then, caution would remain necessary. Atmospheric records are shaped not only by emissions but by circulation, removal, storage, and feedback. A gas released rapidly may persist briefly or for millennia depending on its chemistry. Aerosols can cool the climate while greenhouse gases warm it. Warming itself can trigger secondary releases from oceans, soils, and hydrates, amplifying an initial change. Thus, the atmosphere is not a passive ledger, it is an active system that transforms the signals passing through it. That transformation is not a weakness so much as part of the evidence, because it reveals scale. A perturbation large enough to move the atmosphere also tends to move temperature, precipitation, weathering, ocean uptake, and ecosystems. In this way, the air becomes the central exchange zone between surface processes and deeper archives. When scientists reconstruct ancient atmospheric disturbance, they're rarely reading one signal in isolation. They're assembling a pattern that includes greenhouse gas proxies, dust loads, sulfur markers, black carbon, metal fallout, isotope excursions, and downstream ecological effects. In the present age, this pattern is clear enough that future geologists would have little trouble identifying a sharp atmospheric departure linked to industrial civilization. Whether anything closely comparable exists in older strata remains uncertain, but the framework is established. The atmosphere is where planetary disturbance becomes mobile, mixed, and widely distributed, and because of that mobility it offers one of the best chances for a brief civilization to outlast its own ruins. Air moves on, but what air carries is often laid down elsewhere with patient regularity, preserved in ice, minerals, sediments, and living proxies long after the sky that once held it has changed beyond recognition. The oceans are slower than the atmosphere, heavier than the air, and far less visible in their full movement, yet they preserve disturbance with exceptional patience. Water covers most of the planet, receives material from every continent, exchanges gases continuously with the sky, and stores heat on timescales that can outlast generations, civilizations, and even climatic regimes. Sediment accumulates on continental shelves, in estuaries, in enclosed basins, and across the deep sea floor, where tiny particles descend through darkness and settle in ordered sequence. Shell fragments, clay minerals, organic matter, volcanic ash, soot, pollen, metals, and chemical precipitates all enter this marine archive. Unlike many landscapes on land, where erosion can quickly strip away a surface, parts of the ocean floor gather evidence in relative quiet, in low-energy settings, especially where oxygen is limited and biological mixing is reduced. The sea can preserve thin layers with unusual clarity. This makes the oceans one of the best long-term memories available to Earth system science. For the question of ancient industrial traces, that memory matters because industrial change rarely remains confined to land. Rivers deliver eroded soil, fertilizers, sewage, heavy metals, microplastics, and combustion residues into coastal waters. Atmospheric fallout brings sulfur, nitrogen, black carbon, trace elements, and airborne particles far offshore. Rising carbon dioxide dissolves into the surface ocean and alters its chemistry. Warming changes circulation, stratification, and oxygen content. In other words, the sea receives both the direct waste of civilization and the indirect consequences of altered climate and altered air. Once these inputs enter the marine system, they become part of a network of reactions and transports that may ultimately leave clearer geological signals than the original places from which they came. One of the most important of these signals is acidification. When carbon dioxide dissolves in seawater, it forms carbonic acid, which lowers pH and reduces the availability of carbonate ions used by many marine organisms to build shells and skeletons. This does not dissolve the entire ocean into acidity, but it shifts a delicate chemical balance. In the modern world, this process is already measurable in surface waters and in the changing saturation state of carbonate minerals. Over longer periods, acidification can be recorded by dissolution surfaces in deep-sea sediments, changes in shell thickness and preservation, and shifts in the composition of carbonate-forming organisms. If a civilization were to release large quantities of fossil carbon rapidly, the oceans would absorb much of that burden and register the change in both water chemistry and sedimentary response. Marine anoxia offers another powerful archive of disturbance. Oxygen levels in seawater depend on temperature, circulation, productivity, and the balance between supply and biological consumption. When warming intensifies stratification, surface waters mix less efficiently with deeper layers. When nutrient input rises, algae can bloom, die, and sink, feeding microbial decay that consumes dissolved oxygen. In severe cases, bottom waters become hypoxic or anoxic, meaning oxygen becomes scarce or absent. Sediments forming under such conditions often preserve dark laminations because burrowing organisms decline and mixing is reduced. Certain trace metals, sulfur compounds, and organic molecules also accumulate in ways that signal low oxygen conditions. In the recent age, nutrient runoff and warming have expanded coastal dead zones. In ancient strata, broader anoxic events have often coincided with warming and carbon cycle disruption. This is important because any large industrial civilization would likely affect the sea, not only through carbon release, but also through intensified nutrient transfer from land, altered erosion, and changed circulation. The ocean would therefore record a compound signal rather than a single isolated anomaly. Microfossils deepen this memory. Tiny marine organisms such as foraminifera, coccolithophores, and diatoms are sensitive to temperature, acidity, salinity, nutrients, and oxygen conditions. Their shells accumulate in sediments and can be studied species by species, layer by layer. Changes in abundance, shell chemistry, isotopic composition, and community structure reveal how surface and deep waters responded through time. A rapid environmental disruption often appears in these assemblages as a shift in species dominance, a dwarfing of shell size, a decline in calcifiers, or a turnover in ecological strategy. Because many of these organisms are globally distributed, marine cores from different ocean basins can be compared to test whether a signal is local, regional, or truly planetary. This capacity for correlation makes the sea especially valuable in distinguishing broad Earth system events from isolated accidents of preservation. The ocean is also a sink for particles that have no clear natural pathway in the quantities produced by industry. Fine metal-rich dust, combustion spheres, synthetic polymers, and unusual organics can settle through water columns and become entombed in mud. Their concentration may be highest near coasts or shipping routes, but currents, storms, and biotic transport can scatter them more widely. Burial in cold, dark, low-oxygen sediments may slow degradation and preserve chemical fragments that would weather more rapidly on land. In this way, the sea does not merely receive the leftovers of the surface world, it filters, redistributes, and secures them. yet interpretation remains disciplined by the same rule that governs every earlier section. Natural processes also disturb oceans profoundly. Flood basalts, methane release, orbital forcing, tectonic gateway changes, and asteroid impacts can all warm waters, acidify basins, reduce oxygen, and reorganize marine ecosystems. The sea has witnessed catastrophe many times without any help from technology. What matters, then, is not the presence of marine stress alone, but the pattern and context of that stress. A candidate technosignature would need to appear as part of a larger suite that includes compatible atmospheric, carbon, sedimentary, and perhaps material signals. The oceans by themselves do not prove intention. They do, however, preserve consequence with unusual depth and breadth. They turn invisible gases into dissolved chemistry, land-based erosion into layered mud, ecological stress into microfossil turnover, and broad planetary imbalance into a sedimentary memory that can endure far beyond the structures that once stood on shore. In that sense, the sea functions as both witness and archive, receiving the washed-down remainder of whatever reshapes the world above it, and storing that remainder in quiet layers that accumulate long after the visible drama has passed from sight. Climate disruption appears in geology as pattern rather than weather. No storm, drought, or heat wave survives as a single preserved event across most of the deep record. What survives is the accumulated consequence of many changes working together through time. Temperatures rise or fall, rainfall belts shift, glaciers advance or retreat, sea level adjusts, vegetation reorganizes, erosion speeds up or slows down, and oceans store or release heat in new ways. These changes leave marks in ice, sediments, isotopes, fossils, cave deposits, soils, and shorelines. When scientists reconstruct ancient climate episodes, they do not recover the day-to-day experience of those worlds. They recover structure. They see the pace of warming, the duration of instability, the spread of aridity or humidity, the strength of ocean circulation, and the timing of recovery. This is especially important when trying to distinguish natural climate upheaval from something that might resemble industrial forcing, because the question is not simply whether the planet warmed. Earth has warmed many times. The deeper question concerns timing, rate, feedback, and the full package of associated changes. In the modern world, greenhouse warming caused by industrial emissions is unusually rapid on a geological scale. Carbon dioxide and methane are rising fast. Surface temperatures are increasing. Oceans are absorbing heat. Glaciers are losing mass, and sea level is rising. These shifts are accompanied by acidification, changing rainfall, expanding heat extremes, and movement of climate zones. Future geologists would not need to know the names of fuel types or technologies in order to notice that a sharp climatic perturbation occurred. The sediments, ice, and chemical archives would already carry that information. The challenge comes when older intervals show some of the same broad features. Rapid warming events have happened before. The Paleocene-Eocene thermal maximum, for example, shows a strong negative carbon isotope excursion, significant warming, ocean acidification, ecological migration, and a long recovery. Other hypothermal intervals, though smaller, reveal repeated pulses of carbon and climate disturbance. Much earlier, the end-Permian crisis brought extreme warming, oxygen loss, ecosystem collapse, and prolonged environmental stress. These ancient episodes demonstrate that Earth's climate system can shift suddenly when pushed hard enough. At first glance, such events can resemble the broad outline of industrial forcing, yet resemblance does not erase difference. One of the most important differences lies in trigger. Natural hypothermals are generally linked to volcanism, tectonic change, methane destabilization, or feedbacks internal to the Earth system. Their forcing may be large, but its origin is usually rooted in known planetary processes. Industrial forcing, by contrast, begins with deliberate extraction and combustion of ancient carbon, followed by additional effects from land transformation, aerosols, fertilizers, and synthetic compounds. The climatic result may overlap with natural disturbance, but the associated residue can differ. A purely climatic reconstruction might show only warming and recovery. A broader Earth system reconstruction might also show unusual particles, pollutants, radionuclides, accelerated nitrogen cycling, or synthetic materials. This is why climate patterns alone cannot identify technology, though they remain indispensable to the search. Rate also matters. Geological records do not always preserve exact yearly pacing, yet they often reveal whether a change was abrupt relative to background conditions. A temperature increase spread over hundreds of thousands of years behaves differently from one concentrated into a much shorter interval. Biological communities, weathering systems, and ocean circulation respond differently when pressure is imposed rapidly. Industrial climate forcing is notable because it compresses a large perturbation into a very short window. In deep time, the closest analogues still often unfold more slowly than the modern rise now underway, even after allowing for the blurring of ancient records. That does not rule out the possibility of an older short-lived pulse, but it raises the bar for comparison. A convincing match would need to show not just warming, but unusually rapid onset relative to the resolution and context of the archive. Recovery patterns provide another clue. After a carbon pulse, Earth does not instantly return to baseline. Weathering of rocks, burial of carbon, ocean uptake, and ecological reorganization slowly draw the system back. This means climate recovery can last tens of thousands to hundreds of thousands of years, depending on the magnitude of the disturbance. In ancient events, the shape of recovery helps scientists infer both the size of the forcing and the feedbacks involved. If an event reflects an industrial pulse, the initial rise may be geologically sharp, but the planet's recovery would still follow these slower natural pathways unless continued intervention modified it. A civilization capable of sustained climate engineering could in principle produce a more complex pattern, perhaps alternating forcing and counterforcing through aerosols or atmospheric modification. Yet this remains speculative unless clear supporting evidence appears in the record. Presently, most known ancient climate disruptions are explainable without invoking deliberate management. Climate archives also preserve the geographical spread of disturbance. Pollen and plant fossils record vegetation shifts on land. Loess and dune deposits reveal changing winds and aridity. Glacier advances and retreats leave moraines, isotopic changes, and sea level responses. Speleothems show altered rainfall seasonality, lake levels rise or fall, marine cores capture changes in temperature gradients and circulation strength. When many of these proxies align, they reveal not only that climate changed, but how the planetary system reorganized. This broad reorganization matters for the Silurian question, because industry would not warm the world in isolation. It would influence precipitation, fire regimes, erosion, marine oxygen, and habitats. In that sense, climate disruption is a mediator. It connects emissions and chemistry to biological and sedimentary outcomes. It spreads the signal into multiple archives that can later be compared. The core difficulty remains disciplined interpretation. Earth can produce rapid warming without civilization. Earth can produce feedback cascades, extinctions, and acidification without directed technology. What scientists seek is not a climate anomaly by itself, but a climate anomaly embedded in a larger pattern that exceeds what ordinary natural forcing explains comfortably. Until such a pattern is found, ancient warming events remain powerful analogues and warnings rather than evidence of lost industry. Even so, they teach a valuable lesson. They show that climate is one of the most sensitive planetary systems and one of the most enduring recorders of disruption. If intelligence ever altered Earth at scale, climate would almost certainly have carried that alteration outward, translating local acts of extraction and combustion into a global rearrangement of heat, water, ice, and life that stone and sediment could continue to remember long after the source had disappeared. Mass extinctions are among the strongest interruptions in the history of life, and because they affect whole ecosystems rather than single lineages, they provide one of the clearest ways to examine how planetary crises unfold. In the rock record, an extinction is not simply the disappearance of certain fossils. It is a coordinated biological contraction tied to environmental change across land and sea. Species that once seemed secure become rare and then absent. Food webs shorten. Reef systems weaken or collapse. Forest structures shift. Recovery, when it comes, begins with a reduced cast of survivors and proceeds unevenly across habitats. This makes extinction boundaries especially valuable to Earth system science, because they compress chemistry, climate, ocean conditions, and ecology into a single interval that can be traced in many places. 5 major extinction events are commonly recognized in the history of complex life, though many smaller crises also occurred. The Endordovian extinction is closely tied to glaciation, sea level fall, and later warming. The late Devonian losses involve prolonged environmental instability, ocean anoxia, and ecosystem restructuring. The Permian extinction, the most severe known, coincides with enormous volcanism, extreme warming, acidification, and oxygen loss. The Triassic extinction also links strongly to volcanic outpourings and carbon cycle disturbance. The Cretaceous extinction is associated with the impact of a large asteroid, with additional environmental stress likely influenced by volcanism already underway. In each case, the leading explanations rely on natural causes, and those explanations are supported by multiple lines of evidence. This matters because the temptation to attribute dramatic biological turnover to hidden agency is strongest where the losses are most severe. Scientific discipline requires the reverse approach. The more dramatic the event, the more carefully natural mechanisms must be tested before any unusual alternative is entertained. Extinction patterns can still inform the search for technosignatures, not because they point readily toward lost civilizations, but because they show what planetary disruption does to life at scale. A civilization powered by large energy flows, heavy extraction, and widespread chemical alteration would not leave its signature only in rock chemistry. It would also place selective pressure on ecosystems, habitat fragmentation, warming, acidification, nitrogen loading, toxic releases, and introduced materials would all shape survival and decline in the modern world. This is already visible in biodiversity loss, changing migration, coral bleaching, altered species ranges, and extinction risk. Future strata will likely record a biological response to industrial disruption, even if individual human structures do not survive. This makes extinctions and near extinctions an important comparative field. They reveal which biological signals accompany rapid planetary stress, and how such signals differ depending on cause. Selectivity is one of the key concepts here. Not all extinction mechanisms affect life in the same way. Cooling stresses tropical specialists and shallow marine communities differently than warming does. Acidification harms calcifying organisms more directly than organisms without carbonate structures. Oxygen loss strongly affects bottom-dwelling marine fauna. Wildfire regimes, darkness from impact dust, and collapse of food sources all produce their own patterns of vulnerability. When paleontologists study an extinction, they look not only at how many groups vanished, but which groups vanished first. which survived, and how ecological roles shifted afterward. This selectivity helps constrain the underlying mechanism. A mass extinction caused by volcanism and warming leaves a somewhat different ecological fingerprint than one triggered mainly by impact winter. If an ancient industrial disturbance ever reached extinction scale, it would likely produce a compound selectivity pattern reflecting warming, acidification, habitat loss, pollution, and disrupted nutrient cycles together. That possibility is scientifically interesting, but it does not erase the fact that known extinction events already have strong natural explanations. The Permian crisis offers a good example of how multi-causal natural disaster can appear almost overwhelming in scope. The Siberian Traps eruptions released enormous volumes of lava and greenhouse gases, while heating of organic-rich sediments likely amplified carbon release. Marine anoxia spread, temperatures rose sharply, acidification stressed shell-forming organisms on land, forests and food webs destabilized. The resulting extinction was catastrophic, yet it remains intelligible through interacting natural mechanisms. The Cretaceous boundary shows another style of crisis. There, shocked minerals, a global iridium layer, spherules, soot, and the Chicxulub crater together provide converging evidence of a major impact. The biological effects, including collapse of photosynthetic productivity and food chains, follow from that event with strong coherence. These case studies matter because they show how much evidence is needed to establish cause. An industrial interpretation would require equally strong coherence, not merely a puzzling severity or an abrupt boundary. Recovery after extinction also provides insight. Natural mass extinctions are often followed by delayed rebounds, opportunistic species, simplified ecosystems, and long intervals before diversity fully returns. The pace depends on the scale of environmental damage and how quickly stable conditions are restored. This helps distinguish sudden killing from prolonged stress. A single instantaneous blow can remove many species quickly, but sustained environmental disruption can continue suppressing recovery for a very long time. Industrial forcing, were it large enough, might do both by creating immediate toxicity in some settings and prolonged climate or chemical stress in others. Again, the modern world offers a limited but sobering example. The present biodiversity crisis is not yet a completed mass extinction in geological terms, but it shows how coordinated pressures across climate, chemistry, habitat, and extraction can accumulate into a major biological signal. The lesson from extinction studies is therefore careful rather than sensational. Extinction boundaries are powerful archives of planetary consequence. They reveal how the Earth system translates disturbance into biological loss. They also demonstrate that natural processes alone are capable of producing devastation on the largest scales known. Because of that, mass extinctions do not serve as easy evidence for prior civilizations. Instead, they serve as a standard of comparison. They show what genuine global crisis looks like in fossils, sediments, and geochemistry, and they set a demanding threshold for any claim that something more than volcanism, impact, climate feedback, or ocean change is required. In that demanding framework, extinction becomes less a mystery of hidden intention and more a test of explanatory rigor, asking whether the full pattern of loss, selectivity, and recovery can be accounted for by the planetary forces already known to operate across deep time. The fossil record is often imagined as a continuous chronicle, a stone-bound library in which every age of life has been carefully shelved in order, waiting only to be opened and read. In practice, it is far less complete and far more selective. Most organisms are never fossilized at all. Soft tissues decay quickly. Scavengers disturb remains. Microbes break down cells. Currents scatter bones and shells, and acidic soils dissolve what might otherwise persist. Even when remains do enter sediment, later erosion may remove the deposit entirely, heat and pressure may alter it, or tectonic movement may carry it into regions where it is no longer accessible. The result is a record built from rare success rather than from routine preservation. Fossils are not the default outcome of life. They are exceptional survivors of a process that usually ends in disappearance. This matters greatly when considering whether gaps in the record might conceal evidence of something as brief and localized as a technological civilization. A missing page in geology is not unusual. Missing chapters are not unusual. Entire libraries are absent from many regions. The incompleteness begins with environment. Shallow marine settings often preserve hard-shelled organisms relatively well because sedimentation can be steady and burial gentle. Floodplains may preserve bones, footprints, and plant fragments under the right conditions, yet just as often they rework those materials repeatedly before final burial. Mountain slopes are generally poor archives because erosion dominates over deposition. Tropical forests, despite immense biodiversity, tend to preserve poorly in many cases because heat, moisture, and acidic conditions speed decay. Deserts can preserve tracks or bones for a time, but shifting winds and intermittent floods can remove them again. The fossil record is therefore uneven not only through time but across landscapes. What is abundant in one environment may be nearly absent in another, and this unevenness can create the illusion of sudden appearance or disappearance even when a lineage actually persists elsewhere in unsampled settings. Sampling adds another layer of distortion. Geologists and paleontologists do not have equal access to all ages and regions. Some rock units are widely exposed and richly studied. Others lie buried beneath younger deposits, offshore, beneath ice, or in politically and logistically inaccessible places. A famous formation may yield tens of thousands of specimens because generations of researchers have worked there carefully. Another interval of equal biological importance may remain poorly known because exposures are sparse or preservation is difficult. Scientific understanding therefore grows through patches of clarity, separated by broad zones of uncertainty. This is not a weakness of the discipline so much as a property of the material being studied. The archive is fragmentary before anyone begins to read it, and the act of reading depends on what portions of that archive remain exposed. The apparent suddenness of some transitions must be seen in this light. The Cambrian diversification, for example, represents a genuine and profound biological expansion in the fossil record, yet its apparent abruptness is shaped in part by the increased preservation of hard parts and by the uneven sampling of earlier soft-bodied forms. Likewise, extinction boundaries may seem razor-sharp in some sections and more gradual in others, depending on sedimentation rate, local ecology, and resolution. Gaps do not automatically imply missing civilizations or hidden episodes of advanced life. More often they reflect ordinary geological incompleteness. This caution is essential because the human mind is naturally drawn to narrative completion. Faced with silence in the record, it seeks a dramatic missing cause. Science proceeds differently. It first asks how much silence is expected even in the absence of any extraordinary event. The answer is often a great deal. Taphonomy, the study of what happens to remains from death to discovery, explains much of this silence. Bodies fall apart, bones are chewed, transported, fractured, and weathered. Shells dissolve. Plant tissues compress into faint films or vanish entirely. Even footprints, burrows, and nests are fragile records of behavior that survive only if buried quickly and protected from later disturbance. Material culture, were it to exist in a deep time setting, would face the same or greater difficulties. Wood rots, textiles decay, metals corrode, structures collapse and are reworked into rubble, then into sediment, over millions of years. The chance that recognizable tools or buildings would remain in ordinary surface settings becomes exceedingly small. This does not mean that every civilization would leave no trace. It means direct traces would be rare, and absence of direct traces would not be surprising. The stronger search therefore turns again toward indirect signatures that do not depend on preserving intact objects. Broad disturbances to carbon, nitrogen, metals, synthetic compounds, fire frequency, sediment delivery, and extinction risk have a better chance of outlasting the visible forms that caused them. The fossil record, in this context, is most useful not as a place to hunt for lost machines, but as a sensitive recorder of biological response to planetary change. If an industrial society reshaped climate, oceans, soils, and atmosphere, the biosphere would respond. Species ranges would shift. Calcifiers might decline under acidification. Communities adapted to stable climates could fragment. Opportunistic species might expand. Pollen assemblages would change. Marine microfossils would register warming and oxygen stress. These are the kinds of patterns the fossil record can preserve more reliably than any direct testimony of culture. Even then, interpretation must remain restrained. Biological disturbance alone cannot identify technology because volcanism, impacts, orbital change, and tectonic reorganization can produce similar effects. What the fossil record offers is context and consequence. It shows how life reacted, how selective the stress was, how fast recovery unfolded, and whether ecological restructuring aligns with known physical drivers. In this way, the incompleteness of fossils becomes not merely a limitation, but also a guide. It teaches what not to expect and where stronger evidence must come from. It advises against treating every gap as a secret chamber. It reminds the search to focus on durable system changes rather than on the survival of recognizable artifacts. The record of life is torn, weathered, and partial. Yet within that partiality it still preserves one of the clearest truths in all of geology. When the planet changes deeply enough, life changes with it, and those changes can remain legible even when the original cause has long since vanished from sight. Ancient materials survive in the geological record according to the same rules that govern all buried matter, yet manufactured substances present a special challenge because they are designed for function rather than for preservation. A metal alloy may resist corrosion for a time, but burial chemistry eventually attacks it. Glass can endure for long spans, but it fractures, hydrates, devitrifies, and mixes with sediment. Ceramics often survive better than many organics, though they too can weather, break, and lose their original context. Plastics are durable on human timescales, yet even they fragment, oxidize, and alter chemically under sunlight, heat, pressure, and microbial action. This means that if a technological civilization vanished and enough time passed, its manufactured world would not remain as a neat collection of recognizable objects. It would instead be translated into altered mineral assemblages, unusual particle morphologies, and chemical residues whose significance would depend on context. The key scientific question is therefore not whether tools or devices would survive in familiar form, but which classes of material are most likely to leave a detectable anomaly after burial, deformation, and deep time. Metals provide an instructive beginning. Pure native metals are uncommon in most natural surface settings, and many industrial alloys combine elements in precise ratios that do not usually occur together in ordinary ore formation. Stainless steels, aluminum alloys, specialty titanium blends, and rare earth magnets all depend on concentrated extraction and refined manufacturing pathways. Once buried, these materials corrode, oxidize, crack, and sometimes transform into new mineral phases. Yet corrosion is not disappearance. A rusted alloy may lose its shape while preserving a peculiar concentration of chromium, nickel, molybdenum, vanadium, cobalt, or rare earth elements in association with textures that do not resemble standard natural mineralization. If enough of such material entered a sedimentary basin, the result might be an unusual geochemical horizon rather than an intact artifact. This is especially true where industrial debris becomes fragmented, transported, and sorted by water. In such settings, the original object yields to a population of particles and altered grains, and the geological question becomes whether their chemistry, morphology, and scale of occurrence exceed ordinary background processes. Ceramics and glass may fare differently. Fired clay, bricks, advanced refractories, fiberglass, and engineered glass all begin with thermal processes that change minerals profoundly. Their crystalline and amorphous structures can differ from those of naturally baked clays or volcanic glasses, though distinction is not always simple. A shard of bottle glass broken and buried for a long time may eventually resemble an odd silicate fragment, unless associated with a broader assemblage of human-made material. On the other hand, a widespread concentration of melted silicates, high-temperature slag fragments, and compositionally unusual glassy particles could point to sustained industrial heat, rather than isolated natural fire. The same applies to industrial slags, those dense, chemically altered residues left after metal extraction and smelting. Slag can preserve vesicles, metallic droplets, and mineral combinations that betray intense thermal processing. In future rocks, a slag-rich horizon would not look like a natural lava flow, yet identifying it in great antiquity would still require care because volcanism also produces glass, vesicles, and metal-bearing phases. Once again, context would carry much of the argument. Manufactured polymers pose a more difficult but also more intriguing case. Modern plastics are varied in structure and behavior. Some become brittle quickly under ultraviolet light, while others persist longer in dark or cold settings. Buried in anoxic sediment, fragments may avoid rapid oxidation and remain as recognizable microscopic particles for extended periods. Over much longer spans, however, polymer chains break down, additives leach, and the original material becomes altered. The likely long-term legacy of widespread plastic use is therefore not a world of pristine preserved bags and containers, but a stratum enriched in microplastic residues, unusual carbon-rich fragments, and perhaps chemically distinctive degradation products. If polymers entered sediment in great abundance and burial happened fast enough, some traces might survive in forms still separable from ordinary organic matter. Yet the deeper into time one looks, the more likely it becomes that such substances are transformed beyond direct recognition. The signal, if it persists, would probably be statistical and stratigraphic rather than object-based. Concrete adds another category. It is sometimes imagined as artificial rock, and in many ways that description is apt. Cement hydration binds sand and gravel into a durable mass with characteristic pores, mineral phases, and reinforcement associations. Buried concrete can fracture, dissolve partially, recrystallize, and eventually blend into rubble and sediment, but it does not instantly revert to nature. Its chemistry remains distinctive, especially where large volumes are concentrated in urban deposits, foundations, and coastal infrastructure. Future geologists could plausibly identify such deposits as abrupt masses of anthropogenic lithology, human-made rock, in very deep time. Individual structures might vanish, but a horizon of concrete rubble mixed with metals, ceramics, glass, and asphalt-derived residues could still form an identifiable material signature. The same principle extends to asphalt and bitumen products, which may weather into carbon-rich layers associated with mineral grains, combustion residues, and traffic-related particles. Even advanced materials engineered for high performance would ultimately face the same geological filter. Composites, semiconductors, carbon fibers, and specialized coatings are technologically sophisticated, yet sophistication does not guarantee persistence. Semiconductor wafers break and weather, coatings delaminate, composite resins degrade. Carbon fibers may outlast some matrices, but their broader preservation depends on burial conditions and concentration. What matters most is abundance and distribution. A rare advanced material used in specialized devices may leave almost no detectable trace at planetary scale. A common material used in roads, packaging, buildings, energy systems, and transport has a much greater chance of entering the stratigraphic record. This is why the search for ancient technosignatures focuses less on extraordinary single objects and more on widespread material classes that intersect with mass production and broad dispersal. Nature, of course, can still imitate aspects of manufacture. Lightning fuses sand into glassy fulgurites. Impacts create shocked minerals and melt products. Volcanism generates glass, ash, and metal-rich particles. Hydrothermal systems concentrate unusual elements. Diagenesis can build surprising mineral forms after burial. Because of this, no ancient material anomaly is persuasive on appearance alone. It must be judged by combination, scale, and setting. Manufactured substances would likely survive not as a museum layer of obvious tools, but as an abrupt and unusual material package. A pulse of altered solids, persistent fragments, and redistributed elements that sits awkwardly within the expected grammar of natural deposition. If such a package ever appears in genuinely ancient strata with the right coherence and correlation, it would deserve great attention. Until then, the study of material persistence remains a guide to what deep time tends to spare, what it tends to erase, and how technology is translated into stone after its original purposes have been forgotten. Radioactivity leaves some of the most distinctive signatures in geology, because isotopes decay according to well-understood physical laws and produce daughter products that can be traced long after the original event has passed. This makes nuclear processes unusually legible in the rock record compared with many other forms of activity. A volcanic eruption may leave ash and gases. A biological bloom may leave organic-rich mud. A metalworking culture may disperse elements and altered particles. Nuclear reactions, by contrast, can generate isotope ratios and nuclide distributions that are difficult to confuse with ordinary background conditions once they are measured carefully. For this reason, any discussion of ancient technological traces eventually reaches the question of nuclear signatures. If a civilization developed reactors, weapons, isotope separation, or large-scale nuclear chemistry, some part of that activity could in principle remain detectable for very long spans. The first step in thinking clearly about this subject is to understand that nuclear activity is not always artificial. Nature can produce its own reactor under special circumstances. The best-known example is the Oklo phenomenon in Gabon, where about 2 billion years ago certain uranium-rich deposits achieved natural chain reactions when groundwater moderated neutrons under favourable conditions. These ancient natural reactors operated intermittently and left behind altered isotope ratios in uranium and fission products. Their discovery was scientifically profound because it demonstrated that geological settings can produce sustained nuclear reactions without technology. This matters greatly for any search for ancient industry, because it shows that unusual nuclear signatures are not automatically evidence of civilization. Nature has at least one documented pathway to create them, Scientific caution therefore begins by separating what kinds of isotope anomalies can arise through natural concentration, moderation, and decay, and what kinds would be far harder to explain without engineered processes. Modern nuclear activity leaves a broad suite of markers. Nuclear weapons tests produce fallout containing radionuclides such as cesium, strontium, plutonium, and other isotopes that become dispersed globally through the atmosphere. Reactor operations and fuel processing can release characteristic isotope mixtures, while accidents or waste disposal add more localized patterns. Some of these isotopes decay quickly, but others persist for many thousands or even millions of years depending on half-life. Beyond the isotopes themselves, nuclear events can alter surrounding minerals, melt materials into glasses, create neutron activation products, and impose abrupt chronological markers that future geologists could correlate widely. The mid-20th century radionuclide pulse is one of the clearest possible boundaries in the recent stratigraphic record, because it is both sharp and globally distributed. If anything remotely comparable existed in much older strata, it would deserve immediate scrutiny. Yet deep time complicates the picture. Short-lived radionuclides vanish after enough time, leaving only daughter products or altered isotope balances. Rocks may be buried, heated, weathered, or chemically altered, which can redistribute some products and blur original patterns. Uranium itself is mobile under certain redox conditions. Groundwater can transport dissolved species, and metamorphism can reset or partially reset mineral systems. A genuine ancient nuclear event could therefore become difficult to recognize directly after millions of years. The most durable clues would likely be anomalous isotope ratios preserved in resistant minerals, strange concentrations of certain daughter products, or large-scale patterns repeated across separated localities in ways that resist natural explanation. This returns the discussion to correlation and coherence. One odd measurement in one deposit is rarely decisive. A consistent pattern across multiple archives is far stronger. Reactor technology and weapons technology would not leave identical records. A reactor concentrates fuel, moderates neutrons in particular ways, and produces characteristic fission products depending on design, burn-up, and containment. Weapons detonations impose extreme temperatures and pressures, scattering fallout broadly or locally depending on yield and environment. Underground detonations can create vitrified cavities, fracture zones, and melt products. Atmospheric detonations spread fine radioactive particles widely. A civilization using nuclear energy extensively could therefore leave both clustered and dispersed signals, much as industry more broadly does. Mining and enrichment sites would be local. Fallout horizons could be continental or global. Waste repositories, if they survived in some form, might produce prolonged geochemical anomalies. All of this is physically plausible. The difficulty lies in proving ancient examples when natural uranium systems, cosmic ray exposure, hydrothermal alteration, and ordinary decay chains already produce a rich and complicated background. Scientific method again demands restraint. There are no accepted ancient rock intervals that clearly preserve evidence of prehistoric nuclear technology. Claims sometimes circulate in sensational form, but accepted geology does not support them. What the real science provides instead is a framework for what would count as significant. A convincing case would likely require isotope ratios inconsistent with known natural reactor behavior, preserved in minerals resistant to later alteration, accompanied by stratigraphic context suggesting abrupt emplacement or fallout, and ideally correlated with other non-nuclear technosignatures such as industrial material residues or unusual global chemical disruptions. Without such a package, nuclear claims remain weak. Even so, radioactivity remains one of the most valuable conceptual tools in the Silurian discussion because it clarifies the difference between distinctive signal and dramatic interpretation. The signal may be real, while the interpretation remains wrong. Oklo is the perfect example. The rocks truly record nuclear fission, but the cause is natural. This teaches a broader lesson that applies to all searches for ancient technology. A strange signature must first be understood on its own terms before it is folded into any civilizational narrative. The power of nuclear evidence lies not in its ability to license speculation, but in its precision. Isotopes can be measured, decay chains can be modelled, daughter products can be mapped, natural analogues can be compared. In this way, radioactivity serves as one of geology's sternest judges. It does not reward broad imagination unless that imagination survives contact with numbers, minerals, and physical law. If an ancient technological civilization ever did use nuclear processes at meaningful scale, the rocks would have some chance of remembering, but the memory would not announce itself carelessly. It would appear as a narrow, exacting anomaly, one that would need to withstand the full skepticism of geochemistry before it could be allowed to speak for anything beyond the remarkable, patient inventiveness of nature itself. Antarctica is often imagined as an empty margin of the world, a continent of ice, wind, and prolonged silence. But for Earth history, it functions as one of the most powerful natural vaults on the planet. Its value does not come from mystery alone, it comes from preservation. Snow accumulates, compresses, and stores atmospheric particles and gases. Cold slows many forms of chemical and biological decay. Ice sheets cover older land surfaces, sediments, and bedrock, shielding some records while making them difficult to access. Beneath the surface lie archives of air composition, volcanic fallout, dust transport, ocean interaction, and past climates stretching far beyond written history. For any search concerned with deep-time environmental change, Antarctica is not a place to begin with hidden ruins or dramatic speculation. It is a place to begin with cores, layers, trapped bubbles, buried sediments, and the quiet physical logic of long-term storage. The Antarctic ice sheets preserve one of the clearest direct records of ancient atmosphere available anywhere on Earth for the last several glacial cycles. Deep ice cores reveal past concentrations of carbon dioxide, methane, and nitrous oxide, along with dust, sea salt, sulfate, black carbon, and isotopic signals related to temperature. This alone makes Antarctica central to any study of planetary disturbance. If a civilization were to alter greenhouse gases, combustion products, aerosols, or metal fallout at broad scale, polar ice would be among the best places for those signals to accumulate in stratified order. In the modern world, this is already true. Lead, soot, radionuclides, and industrial chemicals can be measured in polar archives far from their sources. The continent therefore demonstrates an important principle. A remote environment does not stand outside civilization's reach. Through the atmosphere, it becomes one of the clearest receivers of globally dispersed traces. The older and deeper the ice core, however, the more difficult the reading becomes. Flow deformation compresses lower layers, thinning time and complicating interpretation. Basal ice can be disturbed by melting, folding, or contact with the bedrock beneath. Nevertheless, advances in drilling, imaging, and geochemical analysis continue to extend the reach of these records, even where continuous ice does not preserve the deepest possible history. Subglacial sediments, offshore marine cores, and exposed Antarctic rock outcrops contribute additional pieces. These materials help reconstruct when Antarctica was warmer, when forests once grew there, how ice expanded and retreated, and how Southern Ocean circulation linked polar processes to the global climate system. In this sense, Antarctica is not only a frozen archive of the recent past, it is also a gateway into worlds that were once far less icy than today. That broader context matters for the Silurian question, because any ancient industrial signature preserved in Antarctic records would likely appear not as architecture but as atmosphere, dust, chemistry, or unusual particles carried from elsewhere. The most plausible Antarctic technosignatures are therefore indirect. One would look for anomalous greenhouse gas patterns, abrupt isotope shifts, fallout-like distributions of metals or radionuclides, synthetic compounds preserved in exceptional conditions, or strange microparticles embedded within otherwise ordinary layers. Even then, every interpretation would need to pass through strict comparisons with volcanism, biomass burning, marine aerosol input, meteoritic dust, and contamination introduced during drilling or analysis. Polar archives are powerful precisely because they are so sensitive, and sensitivity always brings the need for careful separation of signal from noise. Subglacial and nearshore sediments add another dimension. Beneath the ice sheet lie ancient landscapes, lakes, and sedimentary basins that were once exposed to open air or shallow marine conditions. These buried environments may preserve pollen, spores, organic molecules, mineral weathering profiles, and evidence of past fresh water or marine ecosystems. If Antarctica ever experienced episodes of widespread industrial fallout during warmer intervals in deep time, some fraction of that material might have been incorporated into such sediments and later protected by advancing ice. Offshore cores taken from the continental margin are especially valuable because they collect material eroded from the continent and delivered into marine settings where stratigraphy can remain clearer than on the ice-scoured land surface itself. These marine archives can show when Antarctic vegetation changed, when glaciers advanced, and how dust and ocean chemistry shifted in step with global events. In practical scientific terms, this makes the Antarctic margin one of the best places to test whether broad atmospheric or chemical anomalies reach the far south during candidate intervals of ancient disturbance. The continent also reminds the search to stay physical. Polar exploration has long attracted legends of hidden structures and vanished civilizations, yet accepted science does not support such claims. Ground-penetrating radar, seismic imaging, satellite gravimetry, and drilling reveal bedrock topography, subglacial lakes, mountain ranges, and sediment basins, not confirmed remains of ancient cities. This distinction is important because Antarctica's real scientific value is often greater than the fantasies attached to it. One does not need buried temples to make the continent extraordinary. It is already extraordinary as a stable collector of atmospheric history and a partial cover over older landscapes. The question is not whether the ice conceals obvious monuments. The question is whether it preserves subtle planetary signatures better than many other places on Earth. The answer to that quieter question is clearly yes. Antarctica, therefore, stands near the inward turn of this exploration as a cold storehouse of distributed evidence. It gathers dust from deserts, sulfate from eruptions, soot from fires, salts from the sea, and gases from the air. It compresses them into layers whose order can often be reconstructed with great precision. It shelters older sediments and ancient surfaces beneath immense weight and low temperature. It anchors the modern climate system while also preserving records of climates that were radically different. If a brief civilization ever altered the planet in ways broad enough to enter air and ocean, the Antarctic archives would offer one of the best chances for some trace of that alteration to survive. Not as a direct memory of culture, but as a remote and exacting witness, written in cold layers that continue to accumulate long after the original sources of disturbance have passed away. Biosignatures and technosignatures are both ways of reading a planet. Yet they ask different questions of the same evidence. A biosignature is a sign that life has altered its environment in a measurable way. Oxygen in strong disequilibrium with methane, large seasonal changes linked to vegetation, distinctive organic molecules, isotopic fractionation associated with metabolism, and sedimentary structures shaped by microbial communities all fall within this broad idea. A technosignature, by contrast, is a sign that intelligence has gone beyond metabolism and ecology into directed transformation. It implies energy use organized through tools, large-scale matter transfer, engineered chemistry, or intentional communication. In practice, the boundary is not always sharp. Life itself can be a planetary force of astonishing scale. The rise of oxygen transformed atmosphere and ocean profoundly, while reefs, soils, and the burial of organic carbon have all reshaped the Earth across immense spans. Because of this, scientists cannot define technology merely as something large or powerful. They must define it through patterns of alteration that are difficult to explain through ordinary biology and geology alone. This distinction becomes especially important when Earth is treated as a model world. The same planet that carries a vast library of biosignatures may also be beginning to inscribe unmistakable technosignatures into its air, water, sediment, and orbital surroundings. The usefulness of comparing these two categories lies in their different styles of persistence. Biosignatures often arise through cumulative, self-sustaining processes. Photosynthesis, methanogenesis, biomineralization, and biological sorting of isotopes may operate continuously over long intervals. Building broad planetary imprints, technosignatures may be more abrupt. An industrial society can produce a sharp pulse of greenhouse gases, synthetic compounds, radionuclides, unusual particulates, and material residues within a comparatively short interval. A biosphere works through evolution and ecology. A technosphere works through extraction, manufacturing, transport, combustion, and design. The two interact constantly, but they do not leave identical records. A world rich in life can still lack technology. A world with technology will almost certainly sit inside a biosphere, whether that biosphere is natural, domesticated, altered, or partly engineered. Thus the search for ancient technosignatures on Earth is never a search in empty rock. It is a search inside a living planet that already produces strong background signals of biology, climate, and geology. The scientific challenge is to identify whether any layer shows the additional imprint of directed industrial activity. One reason this challenge is subtle is that many planetary processes can mimic some aspects of technology. Volcanoes emit gases and aerosols. Impacts spread unusual elements and melt products. Hydrothermal systems create chemical gradients and mineral assemblages. Lightning makes glass. Microbes can concentrate metals, alter isotopes, and produce complex organic compounds. Even large-scale landscape modification can arise through rivers, glaciers, and tectonics rather than through intention. For this reason, technosignatures are usually strongest when considered as suites rather than isolated curiosities. A single odd isotope ratio may be ambiguous. A single unusual particle may be contamination or an unknown natural process. A more persuasive case would involve coordinated anomalies across several domains, such as a rapid carbon shift accompanied by globally distributed combustion residues, synthetic materials, nitrogen disruption, and perhaps radioisotopic evidence inconsistent with known natural pathways. The more independent the lines of evidence, the stronger the interpretation becomes. Planetary scientists already use similar logic when considering exoplanets and moons. They ask whether an atmosphere contains gases in combinations that life would tend to maintain. They ask whether industrial pollutants might ever be detectable remotely. They consider whether night-side illumination, narrow-band emissions, or large orbital structures could one day reveal technology from afar, applied to Earth. This same framework becomes humbler and more demanding. Earth is close enough that direct sampling is possible, which means grand claims must survive laboratory analysis rather than broad remote hints. Yet the framework remains powerful because it organizes the search. Biosignatures tell where life has operated. Technosignatures ask whether any of that life learned to rearrange the planet deliberately through sustained, large-scale systems of energy and matter. In the recent record, the answer is plainly yes. Human civilization is generating a technosignature suite that includes atmospheric greenhouse forcing, synthetic molecules, metal redistribution, concrete, plastics, radionuclides, agricultural nutrient pulses, species translocations, and growing orbital debris. The future geological expression of this suite will not preserve every detail, but the overall package is likely to remain visible. That package provides a calibration point. It shows what one known technological species does to a planet, and therefore gives a reference against which older intervals can be judged. At the same time, it teaches caution. Even now, not every human effect is globally uniform, and not every human-made substance is equally preservable. Some technosignatures are strong but brief, others are widespread but chemically fragile. The geological search must therefore prefer those with both broad distribution and durable retention. This is why the distinction between biosignatures and technosignatures ultimately becomes a distinction between ordinary Earth system cycling and signatures of accelerated design throughput. Technology mines ancient reservoirs, concentrates rare elements, creates novel compounds, and leaves rapid multi-proxy disturbances that exceed the normal pace of many background processes. Life alone changes the world deeply, but technology compresses and redirects those changes in ways that are often faster, more angular, and more materially specific. Even so, the two categories are not enemies. Technosignatures are built on biosignatures. A civilization depends on metabolism, ecosystems, atmosphere, water, and raw biological and geological resources. In the deep record, if ancient technology ever existed, it would appear not as a separate kingdom detached from life, but as a particular phase within a biosphere already underway, an interval when one lineage became capable of reorganizing planetary flows beyond what ordinary ecological interaction would produce. Seen this way, the question is not whether Earth has signs of life. It plainly does. The question is whether any older stratum carries the layered, coordinated and durable excess that would justify speaking not only of biology, but of technology once active on a living world. What science can say at the end of this path is both narrower and more valuable than the larger story often imagined around it. The narrow part is simple. There is no accepted evidence that an advanced industrial civilization existed on Earth before humans. No known stratigraphic interval has produced a coherent package of technosignatures strong enough to overturn the natural explanations already supported by geology, paleontology, geochemistry, and climate science. The major disruptions in Earth history, including rapid warming events, ocean crises, isotope excursions, and mass extinctions, are presently explained through impacts, volcanism, tectonics, orbital change, biogeochemical feedback, and ecosystem collapse. Those explanations are not placeholders awaiting a more dramatic substitute. They are built from decades of converging evidence. This must remain the starting point and the ending point of responsible interpretation. Yet the valuable part begins exactly there, because the absence of accepted proof does not make the question useless. It makes the question clarifying. The Silurian Hypothesis has scientific value because it forces a disciplined examination of what would count as evidence, what kinds of traces industry leaves behind, how long those traces persist, and how easily they can be confused with ordinary planetary processes. It sharpens method even if it never confirms a prior civilization. It also deepens appreciation for the present age. By asking how future geologists might recognize human industry after millions of years, scientists learn which of our activities are likely to endure in the rock record and which will vanish almost completely. Carbon isotope shifts, altered nitrogen cycling, synthetic compounds, concrete-rich deposits, microplastic residues, widespread metal redistribution, radionuclide horizons, extinction pressure, and abrupt climate forcing all stand out as likely long-term expressions. Names, borders, languages, and daily intentions do not. The planet will not preserve biography with fairness. It will preserve disturbance with far greater loyalty. This perspective turns the modern world into both subject and experiment. Human civilization is now creating the very type of stratigraphic pulse that the hypothesis uses as a model. That pulse can be measured in air, ice, seawater, soils, sediments, and the changing composition of living communities. It provides a real calibration for the concept of a technosignature. This calibration matters because it replaces vague wonder with physically grounded expectation. If ancient industry ever existed, its traces would most likely appear not as myths brought to life or monuments waiting under every desert, but as coordinated shifts in planetary systems. They would be stratigraphic, geochemical, climatic, material, and biological before they were architectural. Even so, uncertainty remains in honest places. The geological record is incomplete. Oceanic crust is recycled. Continental surfaces are eroded. Burial alters original materials. Short intervals can be blurred. Remote regions remain undersampled. Some preservable signals may still lie undiscovered in marine cores, polar archives, buried basins, or ancient sediments not yet analysed with the full sensitivity of modern techniques. Science allows this uncertainty, but it does not inflate it. It says only that the search space is imperfect, not that hidden civilizations are therefore likely. This distinction protects the boundary between possibility and evidence. A great many things are possible in principle across deep time. Only a few become persuasive because the record supports them strongly. The question therefore becomes not whether imagination can extend further, but whether future work can define more rigorous tests. Such tests are already visible. Better global comparison of rapid carbon events, finer characterization of industrial-like particles, improved understanding of long-term polymer preservation, more sensitive searches for anomalous isotope packages, and tighter integration between paleoclimate records and material residues can all refine the search. The same tools developed to understand the Anthropocene, planetary habitability, and exoplanet technosignatures may continue to improve how Earth's own past is read. This is perhaps the deepest scientific lesson of the entire inquiry. A hypothesis can be worth asking even when the current answer is negative, because the act of asking reshapes methods, definitions, and standards of proof. In that sense, the search for deep-time technology becomes less a hunt for a lost civilization and more a study of how planets remember disruption. Earth remembers through chemistry, through isotopes, through sedimentary order, through the injury and adaptation of living systems, and through the slow burial of matter that once moved quickly through air and water. These memories are real, but they are not easy. They do not offer certainty where the rocks remain ambiguous. They do not reward desire for wonder unless wonder is patient enough to endure measurement. What remains, after all the layers are considered, is a measured position. Humans may be the first technological civilization Earth has hosted. That is still the view supported by present evidence. But geology also teaches humility. It shows how small a civilization is against deep time, how selective preservation can be, and how much of any world is always lost before it is ever read. The responsible conclusion is therefore calm. The hypothesis remains unproven. The methods it inspires remain useful. The planet keeps its records imperfectly, yet well enough to invite careful reading. In that invitation lies the real significance of the question, not as proof of forgotten empires, but as a disciplined way of understanding what intelligence does to a world, and what traces of that intelligence might still remain when everything visible has already passed into stone. In the quiet perspective of geological time, every civilization is brief, every structure is fragile, and every certainty becomes small against the patient movement of rock, water, air, and ice. The surface world changes quickly, but the deeper archives keep only what can endure transformation. A pulse of carbon may remain, a shift in ocean chemistry may remain, a thin layer of ash, dust, metal, or altered sediment may remain. The visible shape of a city rarely does. This is why the search for ancient technology leads not towards spectacle, but towards subtler forms of reading. It turns cliffs into records, ice into atmosphere, sediments into memory, and extinction into consequence. It asks whether intelligence can be recognized after its own works have been weathered into fragments, and those fragments into chemistry. For now, the answer remains careful and incomplete. No earlier industrial civilization has been established by accepted evidence. The known crises of Earth history still belong to volcanism, impacts, climate feedback, tectonic change, and the many powerful processes of a living planet. Yet the question has done its quiet work. It has clarified what industry leaves behind, what deep time removes, and what a future science might still detect. It has also placed the present world into a longer frame, where human activity becomes not only a lived reality, but a geological signal in the making. So the planet rests as it has always rested, carrying its layered archive beneath forests, deserts, glaciers, and seas. The record is torn, partial, and difficult, yet it is never entirely silent. In the long stillness below the surface, change is stored patiently, awaiting only those careful enough to read without haste, and uncertain enough to let the stone answer slowly.